All right, welcome back. Today we're going to be talking about the fourth chapter, TypeSpecifiers, of Common Lisp, the second language. Okay, so TypeSpecifiers, they're basically there's something we use with type P, type of, F-type. We'll talk about that when we talk. These are cases, right? These are how we describe things using the Lisp type system. The Lisp type system is actually fairly flavorful, with quite a bit of information and use that can be taken out from it and put into use it in different ways. Now, many people think that Common Lisp is an untyped language, and that's not the case. It's actually a highly typed language. It's dynamically typed for sure, but also, depending on the compiler, depending on the specific Lisp that you're using, it actually can even be an extremely well statically typed language. And SBCL, which is probably the most popular of the open source versions, actually it does have very decent static compilation, static typing. And we'll see how the type system works using the type specifiers, or how you set up a type. And then we'll talk a little bit about using the type system to get something out of it as well. All right, so first of all, in Common Lisp, types are named by Lisp objects that are called the type specifiers. Type specifiers, right? There are pretty much break down to two. One is symbol names. These are very specific symbols that represent essentially the actual types that are pre-existent in the Common Lisp system. And then there is also additional symbols that can come about as single name symbols that represent the type, either through creating a new type with def type, or actually the def struct, which is creating structures, or def classes, right? So the truth of the matter is you have the predefined symbols and you have the ones that you can create, which basically all together they end up representing classes of objects. Lists, that's something else. You can also represent the type specifier as a list. Now that list contains within it information that can either combine different types together to make a new type, or it can specialize a type, adding or limiting something about the type in order to make a very unique type specifier, meaning we're going to create a sort of, we have like a DSL here, a language in itself almost, in Lisp, that essentially is going to represent types. Which is pretty cool. So you actually have quite a bit of flexibility of what you can do with the typing within Lisp. Okay, so first of all, type specifiers, the symbol versions, right? So very simple, as I said, those are basically either the predefined versions, right? We're going to see afterwards a chart of all the predefined ones in a moment. And then also those that are created from def struct, and those that are created as a result of def class. And actually, I did forget to mention, but they seem to always get a mismention or non-mention, which are conditions. When we get to conditions, we'll talk more about it. But conditions basically are part of the condition system, which is a sort of a subsystem of the conditions, you might say, is the idea of exceptions. But again, there's a condition system also creates a type of object as well that can be a type symbol. All right, so then we get down to the type specifier list. So again, remember, type symbols one side, type list the other. Those are the two divisions of type specifiers. So now, when we get to type specifier lists, so type specifier is a list. The car of the list is a symbol. So these symbols that we had before, right? Those basically, they're either on their own, they're a symbol type specifier, and when they're a list, they're going to be the first one. They're going to be what opens the door to basically start introducing the subsidiary type information, which comes afterwards, is going to be in that list. And the first thing we start out, though, is essentially with one of the symbols. Okay, so this is actually the little chart I just mentioned about before of the various different symbols that come standard, right? And basically, base 54 of TL2E, you have all the various different symbols, right? Ones that are no longer, and again, all the various new ones as well that were mentioned, and they're all there, right? So basically, in addition to the actual symbol itself, like I said, it's always the car, that's the first member of the list. The rest of the list, which comes to essentially specify details about, meaning adding or limiting that symbol in terms of that. For example, a vector, right? So a vector, is a one-dimensional array. So that one-dimensional array could be of any type and can be of any length. So let's say we want a double float vector of 100 elements, right? So this is the way you would actually reflect. So this actually is a type specifier, right, for a vector double float with 100 elements, right? Well, let's say I want to say double float without saying how many elements. Well, a vector double float and a star sort of just lets you fill in missing information. Or let's say a vector of 100 elements, right? And again, we want to leave out, right, this is what type. Now, by the way, if you noticed, this is a little bit different than other places where you're defining a type, let's say in another language, where the type represents what actually the variable is. That's never really the case, right? So these are how we describe a type, and then we use this to either look and see what's in the variable, what's inside that little symbol like that says I'm XYZ parameter, and well, what is X filled with, right? So I can say I want to ensure, right, and we'll talk about probably maybe next or a future class, we'll talk about the ways we actually ensure and guarantee things. But the point is, if you want to say what's in X, what's in parameter X, then you would say, okay, well, I want to make sure that what's in parameter X is a vector. Then I could just say vector. If I want to say it's a vector with double floats and of 100 elements or no elements or unspecified elements, that's how I could describe the question that I'm asking the Lisp image to come back and tell me, hey, is this that X you just fed me? Is that the right kind of X? Or for that matter, if I want to say, listen, I wrote a really cool function, and I want to make sure that the function, right, doesn't get sent the wrong information. Right, so again, that's where it starts to become a question of implementation within the particular implementation of Lisp you're using, whether or not it can handle that automatically or not. But we can program that sort of, at least the dynamic side of things, and at runtime we can certainly program any sort of limitations. But the point is, we'll talk again about how to activate, use the static dynamic typing. But the point is, this is how we describe the type that we want to ensure, right, that essentially we're getting, or we're giving, or whatever we're doing. This is how we describe the types. And I know I'm repeating myself, but just to make it clear what's going on over here. So this is as we get more and more detailed in what the type is. Okay, so again, so a vector of of any type and of any length, right? So that's how that works, right? And in addition to that, then there's some really cool stuff. You see, the types that you could define in Lisp, right? That this DSL, this language that can describe a type, it actually is quite flavorful, because essentially I can even describe a type in terms of functions. Another function that I can actually write software to define my type, which is really cool. So, for example, satisfies a predicate. So I have to have basically a function that returns a true or false. That basically, based on the particular, that whatever the X is, for example, we feed it into, let's say, number P, and if it's a number, it says true. So satisfied number P means this needs to be a number, right? And that's pretty cool, right? That's actually we actually have a type called number we could use instead. But the point is, that's how that works, right? So that's really, really cool that we have the ability to describe using actual full software and Lisp programs practically, right, actually, not practically, literally, that will actually go ahead and help us describe a type in terms of that, which is really neat. In fact, literally, you can almost make any type in the world just using satisfied and turning around and saying true or false when you're done, which is, again, it's like mind-blowing when you think about it. I mean, for certain languages like Ada are certainly unbelievable in the types of things you can do. It's actually a type-based language, Ada, and essentially everything revolves around the type. I mean, the fact that it's actually typing is the most important part of writing software in that language. But yet, nevertheless, he says, I'm telling you, in some ways, this actually tops it all. And the fact that if you have a right implementation like SBCL that does static typing, you're not far behind the power of that ability to be able to really make sure and ensure that you send a software that's correct from a typing perspective. What's really neat is that there are so many other ways to guarantee correctness in Lisp that the typing doesn't have the same level of importance. In fact, it's quite possible to write software that does not even make use of typing and still ensure the correctness that's necessary. But that becomes an entire another course, another different idea of thoughts and things to go to. Hopefully, when we get through CTL to CLTL, excuse me, we'll maybe look into some of those things. Actually, it's funny. It seems to me that in Lisp, there's a lot of great books about the language, but not so many great books that extend into these areas of what can be done with this incredibly expressive language. Probably because there's almost an infinite number of things that could be done. But whatever, that's a long story. But I'm surprised. They're really the type of engineering books that can be done in this blows my mind. And there are some. There's some amazing ones, right? But again, there's so much more that's not just about the language. Okay, type specifiers that combine. So the cool thing is, not only can I just write some function, this DSL also has all kinds of really cool things. So for example, member object 1, object 2, object 3, basically it's the same thing as like saying, equal, EQL, to anything. So basically I'm saying, let's say I have X, and I want it to be a numerator that can only contain certain symbols. Boom, it's a member. It has one of these symbols, right? That's what has to be X. I mean, that's pretty cool, right? So EQL, it has to only be the only valid, one is this specific one. Now, by the way, we will see afterwards there are combiners like AND. So you could do equal, EQL, and actually you can put together very complex types. So it can be, let's say, type ABC. It can be the X can be a certain symbol, whatever it is, my symbol, and then all of a sudden, and it can also be the numbers from 1 to 5, and it could also be, etc., etc. So you can actually write, like I said, very expressive types that even literally are different types. Meaning because the variable can contain anything, right? So we can go ahead and say, okay, this variable, this parameter, this basically contains either this or this or this. It can be a number, it can be a string that describes a number, that answers to a function that makes sure that that actual string is in fact the description in English of a number. I mean, it's pretty. Anyway, sorry, I just get off on a tangent because I'm so excited. Okay, so again, I can use the word not, and, right? All those combiners that can put together different types and put them together. Now, and or, right, both of those are available. Keep in mind that they start processing as soon as one component does not belong, meaning they're short circuit. So the and or are short circuit. So basically, type 1, type 3, if it satisfies the first one, that's it. We stop, right? Just keep that in mind. The point is. Like for example, and, right? So is guaranteed never to result in error because the function prime p will not be invoked unless the object in question has already been determined to be an integer. So the point is this actually says limit prime p to integers because that's the first thing on the and. So that means, as we said, yes, it is an integer, and it also has to satisfy the prime p function. So again, you can see that you can build up types by first essentially this becomes an exclusion, right? And that reduces everything down to an integer. Then you're only getting an integer to start with. Okay, so or basically same idea as we just mentioned before. That's pretty cool. So type specifiers that specialize. So some types like arrays and vectors, things like that, they actually can have additional information that will limit what can be within that specific type. So an array that's short float, that means we can only take an array with members that are short float. Right, so there are various different ways, like I said, to limit. We'll go through. So array, for example, I can say the element type and dimensions, right? How many dimensions, right? In this case, 3-dimensional arrays of integers, right? Or I can basically then define what each one of the dimensions. So this is 3, right? 3 dimensions, and it has to be what basically going to be a 4, 5, and 6. I mean the number of elements that are possible there, right? The rank. Okay, so let's see. I can say I want a short float with a no rank, which again, when we get into arrays, we'll see that kind of stuff. Pretty cool stuff also. So array character, right? It's not the set of all arrays that can hold characters, right? So it's not every possible array that could hold a character, but rather the set of arrays that are specialized to hold precisely and only characters, right? That's the key here, right? So basically, if I say that this type, it must have a character, nothing else is possible, that's the way I would do it, right? And if I say, if I'm in a static typing type of thing, if I somehow connected this to a specific type and I say, you are limited, this is what you can do, and of course, if it's possible, then the Lisp compiler will then tell me, oh, wait a minute, you just made an array here that's not an array character, and you try to put it into this variable that has been limited to this, right? Okay, so again, we'll get to that when we get to, when we get to it. But as far as just, again, we're just concentrating right now on the language of describing a type. That's the key. Remember this. Don't get too bogged down a word if you don't understand yet what this means, but understand that we're learning the language of how to describe a type. So for example, this is a little bit of a detail that's worth knowing. So I can go, when I do type P, which is check the type of foo, right? What is this thing? And of course the predicate, so is it this? So in other words, is this an array character? So what that means is, is foo basically only hold, is that a variable that has been set to only allow arrays of characters, right? Or we say is, oh, wait a minute, can hold characters, meaning this tells you whether or not the specific, right, in other words, element type of foo, right, is in fact a character type. It can put a character. So this is how I would check to see if I could put in that array. Again, like I said, this is a little more complicated element, and like I said, it's not really used most of this that much, but still worthwhile. Again, the parts that I've pointed out over here and over here, right? These are important little facts to keep in mind. So you decide to go back and look more into this. All right, simple array, vector. Again, element dimensions for the array, element size for the vector, right? That's the automatic. Because remember, dimensions can be either the number of dimensions, or we can use that format where we enter a Lisp with each one of the sizes for each one of the dimensions. So there's only one dimension here. We're going to have to tell that, but we'll just do the size of the vector, meaning the number in the particular first dimension that could possibly be the size, right? So if I can double float, tells me about double float, or I can say any type but has only 5 elements, and so forth and so on, right? And we'll see afterwards you can actually even get more complex, right? So we can basically vectors of integers between 0 and 31, and right? So there are all kinds of neat things you can do with this, as we mentioned. So simple vector size, complex types. Basically, there's more information again you can feed in of the different types. Different parts of the complex numbers, what part is, what the type is for that part. Okay, this is a really interesting one, right? And that is the type description used for a function, right? Now that's pretty cool, right? Basically, here's the thing, right? You can, let's say in general, this says, okay, the function, if I again is this, let's say I'm going to use I'll probably have to show you already how to use this a little bit, but let's say if I want to basically say declaim a function that, say, the first argument is an integer, second argument is an integer, and it returns an integer, right? So this is something that I can do. So let's actually jump into a piece of code, right? So let's take a look at this, right? So I have an interesting function, right? And here I go ahead and I call that function, right? Now what happens is like this. I set the function up. This is actually completely valid. A times B, that's what gets returned from here, right? And let's go ahead and run this, right? So I go ahead and I value it all. Why is that the case? Oh, because I've already made the declaim before in this image. Very funny. Okay, well, let's go ahead and just do this for now then. Okay, fine. Value it all. No problem, right? So basically, take a look at this, right? So I went ahead and I have a function, right? And that function basically, I go ahead and just multiply it. And that's really what goes on over here, 1 times 2. Now, what happens is if I want to put some limits, if I actually want to turn around and say that the only thing that function should receive, I can make a global declaration that basically, proclamation, right? That's the word for it, right? A proclamation using the claim, the macro version of proclaim, right? So the claim basically, I say, listen, I want to go ahead and I want to say that this particular function type, right? Basically, it's a function that has an integer and an integer, and it returns an integer. So, of course, if I try to feed anything into an integer, if I have static typing enabled, like an SBCL, it will actually give me an error when I try this, right? Now, by the way, why would I care about doing this if the compiler couldn't actually turn around and tell me anything? What it can do here is that it can optimize things. It can ensure that the types, right, that are here are optimized. And essentially, of course, it's up to us not to violate the optimization and create a seg fault. But basically saying that if I know that this was only going to be called by a certain type of a certain way, I let the compiler know. So in many ways, this is sort of just a hint to the compiler. Unless you're on SBCL and you've turned on, again, the static typing, where safety is, I think, 2 and above, whatever it is, that basically then it says that, you know, it's going to protect this to make sure that doesn't happen. And it'll even do a static check, not just dynamic check, to make sure that doesn't happen, right? So that's the claim. That would essentially say that that's what this function is. These are the types this function is going to be accepting. And if you essentially use this properly, it will fit this. So this is many ways just sort of a description of what this function should do, right? Okay, again, so that's the case, right? Now, what's interesting over here is we're going to use declare, right? Let's say the other way around. So let's say I have a function and I want to essentially say I'm only going to call the function called MT. Well, that wouldn't even work here. So MYT, sorry. So MYT will only be called, right? Any function named MYT that's below here in this scope, that function, right? If I call it, it's going to be this type. Okay, so what's cool is there's actually two ways basically to control access. Well, control not access, but the means by which we call, and if you have static typing available. But the point, my main point here, like that Avik said, wasn't necessarily go too much into this declare and declaim, but rather just to illustrate the fact that how you would make use of the particular type specifier called a function. It was actually, and you use f type to describe a function, right? Basically, these are parameters, again, are returned, and we can describe how this particular function works. Now, again, this is really not as important as it is in other languages, but the point is Lisp has it. It's there, right? And it does have use, like I said, with the right list system, where you have static typing, then that's great. And even when you don't, then again, these are just giving hints as to how to optimize things. So that this way, and also for you, the user of this particular function, you now know don't call this function without integers, right? And you're always going to get an integer back. I'm promising you're getting an integer back. You feed me 2 integers, I will do it. What I said I will do, I will return with an integer. That's the whole point. Okay. So again, just like we have in our defun, an optional rest key, all these things are possible within the actual excuse me type specifier. Or the keys is another one that's also possible. By the way, the difference between type P and F type over here, F type or just function, is that generally speaking the correct way is F type function. Right, and essentially things change in the standard, etc. So if you can also just use function the way it is, but the correct way is an F type of this function when you're declaring and declaiming. That goes back to what we were doing before. But the point is the DSL is all about creating a specific type specifier is that way. Okay, let's go further. Okay, so you can also do a type. I mean, it says that a certain variable, basically this variable, whatever variable we're declaiming, or declaring, that a certain variable can only hold a function, right? And this means to say a function could be a lambda, it could be a function which has a name, but either way, it's essentially a function that that is going to have types, return values, and so forth, right? In the case of type, you say which the name of the variable name is that is essentially being limited to only this particular function type. So therefore, any reference to that variable, right, var, we're saying we'll find that its value is a function, and that is an error to call this function with an actual argument not specified in type array, the R type. Also an error for the result not to be of the specified value of type, right value type, and that's the guaranteed return value. So thus a type or F type declaration specifier describes type requirements imposed on calls to a function as opposed to requirements imposed on the definition of the function, right? So if you notice when we did our little function over here, right? So declare limits the call, declaim limits, right? But it basically says this is what we can receive. So this is the sender, we basically make a difference, and this is going to be the receiver, we make a difference, right? The key factor here is that this essentially leads to optimizations in the compiler, because we're guaranteeing as the programmer that we're not going to call this function except in this way, right? And except in that way. And here again, we're saying we're not going to make a call to the function MYT basically unless again it's a function with two integer parameters and integer return. And again, as long as safety's on, you know, so SBCL may give us some errors, but most compilers are not going to be statically checking, and essentially they are relying on your promise. So this is really a promise of what the programmer would do, much more than what anything else. It's really a promise about the programmer. But again, this is documentation for us, and this essentially, again, like I said, is something the compiler can use for optimization. Unless again, SBCL, which offers us some additional information, because it can and does post errors to help us again find errors based on static typing. Okay, so all right, so the last values. So again, this is interesting, because this basically, you know, that in Lisp you can return multiple values. So essentially that's how you would express the multiple values in the return type, in other words, of a function. So that would go where the return type would go in a function. So again, that's the value type of the return. So you can use the values, and then you can specify what the multiple values will be returning as well. All right, so this takes us into some additional type specifiers for our DSLs for type specifiers. That is, we can say, okay, this is an integer, and we can specify that it will be within a range, right? We can say, you know, it's modulus, meaning it's going to be an unsigned integer that's going to be from 0 to n-1, right? Signed bytes. So basically, again, we're stating that it's a byte with a sign. Unsigned bytes, irrational, again, within limits, floats within limits, and so forth. Again, all of these things, again, help us to describe, this is the means with which we can describe types. String, we're saying simple size, simple string, again, size, simple string and simple string, and we've seen this also by other places, such as, for example, or simple arrays. What that means is that none of the additional extras that we can do, for example, like you can have a vector that can expand, where you can dynamically change the size of it. So you have none of the extras. It's just a string of bytes. It's just a series of vectors, one after another. And again, it can be optimized to be that way in memory. We don't know how the compiler chose it, but we're saying that this particular, I want to know, is this going to be the type of a string that essentially is not going to change in size, and so forth, the next time I get it. Who knows what you might want to optimize for finding out that particular type. But that's the idea behind the simple versus the versions without simple. Bit vector, again, so we think we did talk about bits and the fact that you'd set up these vectors that represent bits that are actually, again, sort of packed into the small sizes that they can be, a char, an integer, and so forth. All right. Okay, so now we define new types. Okay, so defining new type specifiers, we've already mentioned that. They can be done through a def struct or a def class. They will basically create a new symbol that represents a type. And of course, def type itself, basically, what you could do is you could use this DSL to produce a type and give a name to it. Makes a lot of sense, right? So again, all different little examples, whatever else have you. There's really not much more to it other than the fact, again, that you just give a name to a specific description of a type. What's interesting also, you have type conversion functions. Let's see here. So basically coerce. So given a certain object, you can and you basically and a particular result type you'd like to get out of it, then you'll get results. So coerce of anything to nil is always going to result in a signal because there is nothing but nil in the null type. Let's see here. Any object can be coerced to a type true because everything is true basically, right? Except for null. no, which is a null, right? So that's the case. And let's see, coercion from floating points doesn't exist purposely, and because basically you really need to be doing some rounding. The same thing when it comes from characters and integers. You kind of have to decide how they're going to convert, but the codes or things like that. So again, there are functions provided by Lisp for doing those conversions, and we don't use coerce. Okay, so type of. So type P was how you ask, is it this or not? Yeah, true or false. Type of essentially tries to make a good guess as to what type we are looking at, right? So given X, so what are you type of? And it will return, again, using the various different algorithms to come up with a type. Okay, type, I think we'll basically, we'll call it, okay, I think we'll call it for today. All right.